Okay, super. So, like I said, we're going to talk about sorting. So, overview, the bottom line is that the Chapel standard library sort can now sort a block distributed array, and it's been able to do that since Chapel 2.5. It uses the distributed sort implemented here works with all the supported comparators. I'm going to talk about what those are in a second. The core of it is a most significant digit first radix sort, and I'm also going to tell you what that is. And it uses a new method of tracking subproblems for the MSD radix sort that's efficient for distributed memory. And it's fast, and we'll talk about all of these things. So those are sort of both the bottom line and an overview. So first, we'll talk about radix sort. So a starting point is, let's just talk about how you provide the order you want to sort something when you call the sort function. In the Chapel standard library, you can provide what we call a comparator to indicate the order you want in your sort. And you can do that in three different ways. You could provide a key method, and that'd be for a case like if you're sorting a tuple or a record that has a particular field you want to sort by, you can just return that and go. You can provide a compare method if you only know how to compare two elements to indicate their order. And you can provide a key part method that lets you return part of a key to sort by. So a main example for that is if you have something like a string that's variable length, you can return the ith letter or character in your string. In the key part method, it takes in an integer and it will return something to indicate what that part was, like the ith value of the string, and whether or not it reached the end. In other languages, standard library sorts usually have something akin to the .key method and the .compare method for specifying sort order. Usually you would need to use something like that .key method that returns an integer to trigger a radix sort in a standard library, and then everything else will use a comparison sort. But in Chapel, we're unique because we have this .key part method, and that provides a generalized interface for radix sorting. I haven't seen any other language do that in the standard library, so I feel like we can brag about it. Anyway, in the upcoming parts of this talk, I'm going to use the term key to mean what we're sorting by, even if that doesn't necessarily correspond to all of what we're sorting by the whole time. It's what we're sorting by at the moment. Anyway, on to the next part. Oh, I have to get to there we go. So let's talk about radix sorting. So sorting is often described as having complexity n log n. If you have taken some computer science courses, you would have covered this. There is a theorem that says that's the best you can do. Aside from constant factors, it's going to scale this way. But that bound only applies to comparison sort. So comparison sort is when you have like one of those .compare kind of comparators. If you have something else, like you're just sorting integers, then we can use radix sort. And it's an order n sorting method instead of n log n. And more specifically, radix sorts are normally order k times n, where k is the key length. So for example, if we're sorting integers, if they were 20,000 byte integers, then we would be doing 20,000 times number of elements work to radix sort them. Radix sorting is actually really intuitive and natural algorithm. The core of it, if you think about something in reality, in regular life, I mean, computers are real too, but in regular life, maybe you have some decks of cards, lots of cards, maybe you've got 18 decks or something, and you want to sort them by suit. I don't know why you want to do this. It's a slide. So the idea is make a bucket for each suit. You make a bucket for spades, a bucket for hearts, etc. And then you just go through the deck once and you put the card in the bucket that has its suit. And then after that, you just dump the cards from the buckets out on top of each other in the magical world of slide examples. The cards don't all fall on the floor and they end up in a nice stack in the right order. So, but the idea of putting them into these different buckets is pretty intuitive, and it's a linear process, right? We didn't really have to do any logarithmic kind of work per card or anything like that. So that's a good intuition about how we can get to a radix sorting that's order kn. So building block for radix sorts is something called counting sort. This is what articles and things call it, even though I consider this a building block. It's not really a whole sort. But counting sort is how we can take that slide example of I've got buckets and cards and I would sort them by suit and turn it into an algorithm I can run on a computer with arrays. So we're going to have 3 arrays, an input array, an output array, and a counts array. And what the algorithm is going to do is it's going to go through each element in the input array. It's going to count, and it's going to increment the count for the suit that it found. And then it's going to compute the starting indices in the output array for everything by doing a prefix sum. And then after that, it's going to go through the input array again, and it's going to use the starting positions in the output array, and is going to add to those to know where to put it. And I have an example on the next slide, so we don't have to worry too much about my little bit of code there. So this algorithm can be done in parallel and it's stable. In other words, if you have equal elements, and here if we're talking about sorting by suits or something, maybe there's other elements that we're going to sort by in a subsequent step. So if those elements are equal right now, they have the same suit, then we won't rearrange them. In the rest of this talk, I'm going to call this algorithm partition rather than counting sort. And I'm going to call the regions it produces buckets. And here's an example of counting sort. So here I made a table with a bunch of indices. So this is on the left, the indices are just spots in an array. And then the key is a different suit. And then I've got a value. I just gave them each a letter so that I get an idea where each quote unquote card is going. So then we just count up how many spades are there, how many hearts, etc. We can do that in one pass over the input. And then we do this prefix sum or exclusive scan. In Chapel, the scan keyword is an inclusive scan. So that just means you would need to subtract the first count if you did this with the Chapel scan. And this gives us, all we did here is say, started at 0. And then for the next one, how many before? It was 2. So that's why 2 is here. And then for the next one, how many before? 2 plus 4 is 6. So that's why 6 is here. That's all it's doing. So that gives us the offset into the output array for each section. And then we can go through the input and distribute each of these into the appropriate section while incrementing sort of the current pointer in the section while we're doing that. So now I've shown you how to do this partition operation in linear time, with arrays on a computer. And I don't go through the parallel version of this in my slides, but the parallel version is similar. The key thing to think about is to figure out a start offset for not only for each possible key, which is a suit in this case, but also for each task. So we're going to compute across all the tasks a start position for task 1's spades, task 3's spades, etc., and rearrange the data that way. Okay, so then from there we can go into a least significant digit first radix sort. This is the kind of sort that Arcuda uses. We have those arrays A, B, and C before, and what we're going to do is we're going to use that partition method to sort k-digit numbers. All we're going to do is add in a loop, and we're going to start from the least significant digit partition, and then put the output array back in the input. Some observations about this: we have to have a stable partition. It's going to be parallel if our partition is parallel. And it assumes that all of the array elements have the same number of digits. So if we have strings that have arbitrary lengths, it's unsuitable. You could imagine working around that by padding everything out to match the longest length, but that would make it a lot less efficient. So here I have a quick little example of least significant digit first radix sort. So here's something we'll sort. So in the first step, we're starting with the least significant digit. That's the rightmost one. So I've got all the things that ended in 0 in this section. This one ended in 1, 2, and then these are ending in 3. Now we work by the second digit. And so here I have all the things where the second digit was 0. And you'll notice that these are already in order because it was stable. These ones were in order before. Now if they were in order and they had the same previous digit, now we're in the proper order. So for those two digits, because the partition is stable. Anyway, so we can go on through this process and we get a sorted array. So now I'm going to talk about most significant digit first radix sort, which is significantly more complicated than least significant digit first. What we're going to do is we're going to have the same arrays A, B, and C as before, and we're going to have a queue. And the queue is just going to have a start and end for a region within the array and a current digit position. So we'll start by putting the whole region and digit position 0 into the queue, and then we'll proceed doing this thing while the queue's got anything in it. We pop something from the queue, we partition that region, and then we look at each bucket that the partition created. If there's no more digits in that bucket, nothing to do. If as a small number of digits, we do a base case, we use a comparison sort. Otherwise, we put it in the queue. And then we still have this putting the input array back in the output array business. I'll note that on my slides, both in particular for this most significant digit first radix sort, I'm doing definitely non-optimal data movement between the arrays, but it's better for understanding at first to explain it this way. So a couple observations. We can handle keys with varying lengths. We can handle that key part. When we're doing partition, if we want to handle keys that elements that have their digits available end before other ones, then we can make a region dedicated to no more digits. Another thing that's really important to understand about MSD radix sort is that the number of work items in the queue grows as the algorithm proceeds. So it started with 1, and then we're going to have potentially basically an exponential growth in it for a little while. It's bounded, but it's going to grow rapidly, and each of those work items is shrinking. So this sort of queue situation is difficult to work with in parallel and distributed memory. Here's a little example with most significant digit first radix sort. I made a bunch of little strings of digits here that have varying lengths to kind of convey that. First, we sort by the initial leftmost digit, the most significant digit. So you've got all the things that start with 0. There were none that started with 1. So there's empty region 2 and then 3. And then within each of these groups that has more than one thing, in the next step, I partition it by the next digit. So here, I've got the things that the first two digits were 0 together. Here's 0, 1, there was only one thing. And then the next step, right, this 0, 1, 0, 2, 0, 3, 3, we didn't have to do anything. They're already fine. But this one we needed to sort because I had more than one. So you can kind of get an intuition about why MSD sort is usually more efficient than LSD sort, because this is the same number of passes, but I didn't have to actually do n work in each one of these because we only need to sort some of those regions. Okay, and then what about comparison sorting? So if you have an MSD radix sort, you can build comparison sorting. You can build comparison sorting by creating splitters and then doing a binary search. And then I'm going to start going a little bit faster because I want to have time for questions. So here's the new radix sort. So previously we had a distributed LSD radix sort implemented in our CUDA, but the problem was that couldn't support the .keyPart interface or sorting variable length strings generally because it's an LSD sort, which I already described. I tried to make a distributed MSD radix sort in 2019. There was a talk about that. And that I'll show in performance slides in a second. That's called two-array distributed radix sort. And then recently I worked on this again, and I had the idea to track bucket boundaries with an additional array that I came across another radix sort that was doing that in this reference. So how's that work? Well, we add in an array R of size n that stores 1 byte per element. It's going to store if it's a bucket boundary and also some other information, including which array. If we have a small bucket, we're going to sort it just with comparison sort anyway, and we can scan to find the end of the bucket, so that's fine. If we have a large bucket, we have space, because I didn't use all of the bits in those bytes, to store additional information. This allows us to record all of the information about the state of our progress towards sorting in this array R. And then we have a thing called sort step that makes progress on a region, on a bucket, and then records the state in R. So here's the algorithm. I'm going to skip over this and instead go to an example. Before I go to the example, the trickiest parts was of implementing it was that it needed, so the sort step and partition needed to work at different levels of parallelism. Distributed, parallel, and distributed, parallel, single locale parallel, and serial. And I'm still accelerating a little bit to have time for questions. So here's an example. I've started out with, here's an input array, and then I'm showing you how the array is divided up among the tasks and locales. So the concept is each locale, of course, owns part of the array because that's where it's stored, but within it, each task owns part of the array. So first we do an initial partition, just like the MSD example I showed earlier, and that's where these boundaries are coming from. And then the next thing we're going to do is we're going to sort the regions that cross locale boundaries. So there's one here in my example, and whichever locale has the first element owns it, and so that's responsible for sorting it. Then we do the same thing for buckets spanning tasks, and there's one here that these all start with 0, and there's 2 tasks involved, right? So this task 0, owns this entire bucket, so it's in charge of sorting that. And then after that, we sort all of the buckets, and everything can proceed independently. Yes, okay, and then here's some performance data. It's faster than the previous MSD sort and faster than our CUDA sort on XC, on EX. It competes with an MPI sort on EX, and it is faster than the Arcuda sort on an InfiniBand cluster. And I will leave this slide up and pause for questions, since I've gone slightly over what I had hoped for in the part where I talked to you. But thank you.
Yeah, thanks, Michael.
Any questions?
Daniel, go ahead.
At the risk of sounding completely ignorant, so you're talking about partitioning things across locale boundaries, and there's elements that are, it seems to me like, since the first element in a particular partition is owned by whatever locale the first element, or sorry, a particular partition depends on which locale its first element is on. You need to transfer things between locales. Do you do some kind of aggregation to avoid overheads from individual comms this way?
Yes. It uses aggregators as much as possible, and bulk transfer, sort of the combination of aggregation and bulk transfer to optimize the communication.
Were those explicit aggregators, or was the compiler able to find and insert
I was using explicit aggregators. Like I was saying before, even though I was starting to speed up, the one challenge is if you want to use something like aggregators or optimize, with local blocks or something like that, the code ends up needing to do different things depending on how you're running it, right? So it's harder to have the same code for serial and parallel, even though in concept in Chapel we can do that.
Got it. Thank you.
Awesome. Well, let's give Mike